Alright, this is going to be the first of two videos covering section 3.2. This is the calculus of vector valued functions. And so we're going to compare this with the derivative that we would have defined in calculus 1, and we did the limit definition of derivative. And we say that the function f of x is differentiable at x if f prime of x, which is equal to the limit as h goes to 0, of f of x plus h minus f of x all over h exists. And so if we draw the function f of x, then f of x would be our specific x we're picking on here, would be right there. And then our f of x plus h will be some point on the graph, either to the right or the left. It just, it just depends on what h is, but we'll just assume that it's on the right here. It doesn't really matter for our illustration. And so what we do is f of x plus h minus f of x all over h. That represents the slope of this secant line that I've drawn. And then we let h go to 0, which means that x plus h is going to get closer and closer and closer to x. And so when we find the slopes of these secant lines, they're going to get closer and closer until they're almost indistinguishable from the slope of the tangent line, and that's our derivative. The derivative is an instantaneous rate of change. A secant slope is going to be an average rate of change, so a little bit different there. And then for a vector valued function r of t to be differentiable at a point t is to say that r prime of t is equal to the limit as h goes to 0, rt plus h minus r of t all over h, if that exists. So we can draw a sketch of sort of what's going on here. So here's your vector r of t, and then our r of t plus h, and we're going to let h go to 0, and so r of t plus h is going to get closer and closer to r of t. The green vector I've drawn there is r of t plus h minus r of t. And so as we get closer and closer, we have our whatever our curve is doing following our vector valued function. So it's going to do something like this. So as h goes to 0, this vector r of t plus h minus r of t is going to get closer and closer to a tangent vector. And so a tangent vector we can use for talking about maybe a velocity or speed or something like that. So we're going to get into that a little bit later on in the chapter. All right, so let's look at the differentiation for a vector valued function or functions. For the plane, r of t is equal to the f of ti plus g of tj, where f and g are differentiable functions of t. The derivative, r prime of t, is going to be equal to f prime of ti plus g prime of tj, so it's just the respective components. And then in space, r of t is equal to f of ti plus g of tj plus h of tk, where f, g, and h are differentiable functions of t. Then the derivative, r prime of t, is equal to f prime of ti plus g prime of tj plus h prime of tk. So we're gonna do an example. We're gonna find r of t naught, r prime of t, and r prime of t naught for r of t is equal to the cosine of ti plus the sine of tj, and then t naught is going to be pi over 2. We're going to sketch r of t and r prime of t. So we're going to do all of that here. And so first thing we're going to do is we're going to do a sketch for the r of t equals cosine ti plus sine tj. Okay, so we're just going to fill it out. Cosine of 0 is 1, sine of 0 is 0, cosine of pi over 2 is 0, sine of pi over 2 is 1, cosine of pi is negative 1, sine of pi is 0, and 3 pi over 2, so cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is negative 1, and then all the way around we start over again. And this is going to end up making a unit circle here. Okay. and mine looks kind of like a an egg or whatever. So using your imagination a little bit, it's supposed to be a nice circle, a nice unit circle, and we have the orientation drawn in there. And so we're going to find the value of the function at pi over 2, and then we're going to look at the derivative. So the value of the function at pi over 2 is going to be 0I plus j. So that's just going to be the north pole on the unit circle. So let's find the derivative. So r prime of t, the derivative of cosine is negative sine. So negative sine ti, derivative sine is cosine, plus cosine tj. That's our derivative function. So r prime of pi over 2 is going to be equal to, the sine of pi over 2 is going to be 1, so negative I, and then the cosine of pi over 2 is 0, so we're going to get negative I plus j. And so if we graph that, that's going to give us negative I there. And so you see that negative I is when we're at the top of the unit circle there, following the path is going to the left, and so that gives us our tangent there. We could also find, this is not on here, but let's go ahead and find r prime of pi. R prime of pi would be 0I and then minus j, and so that would give us our tangent there. Okay, so that's pointing to the direction that we're going, or our tangent. Okay, now let's look at the second derivative. I know it didn't ask for the second derivative, but let's find the second derivative, which is negative cosine of ti, and then minus sine of tj. And we're going to find the second derivative at these 2 points. So r double prime at pi over 2 is going to be equal to it's going to be equal to 0I and then minus j. And so remember, second derivative is your acceleration, so our acceleration is towards the center of the circle. And then later on, that'll kind of tell us ultimately where is it going to be turning. So it's going to be turning towards the center. Okay, let's find the second derivative at pi, and the second derivative at pi is going to be I plus a 0j, and so again that's going to be, it's going to be pointing towards the center, or we're going to be turning around that center there. So that'll be interesting stuff later on. Okay, and we're going to do some examples of derivatives and antiderivatives. So let's go ahead and take some derivatives of some vector-valued functions. So we're going to find the derivatives. So the first one is r of t is equal to t to the 3/2 I plus sine squared tj plus the natural log of tk. So we're going to go ahead and take the derivative. I'll put some of the derivative rules up. You might need to review your derivative rules. Hopefully the Cal 1, Cal 2 derivatives and antiderivatives are relatively fresh. If you need a review, just go in and maybe look at your old notes or your old homework and just practice some. Look up some videos on taking derivatives and so forth. So r prime of t, we're going to use the power rule. So the 3/2 comes down, subtract 1 from your exponent, so it's going to be t to the 1/2 power I. Okay, so that is the power rule. So the derivative of x to the n power, the exponent of n comes down as a factor, and you subtract 1 from the exponent, so nx to the n minus 1. Okay. Sine squared of t is composition of 2 functions. The outside function is square. The inside function is sine. That is a composition, so we take the derivative of the outside, so the square would come down, and then your base, which is the sine of t to the first power, and then times the derivative of the base, which is the sine of t. The derivative of the base would be cosine of t, j. So that is your chain rule right there. So the derivative of the composition f composed with g of x is going to be f prime of g of x, and then times g prime of x. Okay, and then lastly, we're going to take the derivative of the natural log of t, which is 1 over t, and then don't forget our k. So the derivative of the natural log of x is 1 over x. Okay, and that's it. So for part B, R of t is equal to t cosine ti plus t sine tj plus tk. And so we're going to be doing a product rule because we have the function t times the function cosine t. So derivative of the first would be 1, derivative of t is 1, and then times the second function of cosine of t, plus the first function t times derivative of the second function, which is the cosine, as derivative of negative sine. Okay, and that is our I component. Okay, and then we're going to do the same thing for the j component. So the derivative of the first function is 1 times the sine of t, plus the first function, which is t, times the derivative of the second, which is cosine of t. Okay, and that's our j component, plus the derivative of t is just 1, or 1k. So we'll put up our derivative of a product. So the derivative of f of x times g of x is going to be f prime of x, so derivative of the first times the second function g of x, plus the first function f of x times the derivative of the second. Okay, so that'd be f of x g prime of x. All right, so let's clean that up. So this is going to be cosine t minus t sine of t I plus sine t plus t cosine t, and that's the j component, and then plus k. Okay. All right, and the last one, second to last one, I got a part D that's going to be on the next slide. So part C, we have r of t is equal to the arc sine of 2t I plus the arc cosine of t j plus the arc tangent of t squared k. So the derivative of the arc sine of u, where u is a differentiable function of x, is going to be u prime by the chain rule, and then 1 minus u squared. So the derivative of the arc sine of 2t, your u would be 2t, so u prime would be 2, and then divided by the square root of 1 minus 2t squared, which would be 4t squared. That's your I. Now, if you can remember the arc sine's derivative, the arc cosine's derivative is very easy to remember. It's the arc sine's derivative, but it's just off by a minus sign. So then the derivative of arc cosine of the differentiable function of x, function u, is going to be negative u prime over 1 minus u squared. So here your u is t, so it's just going to be u prime is 1 over 1 minus u squared, or 1 minus t squared. That's your j component. And then lastly, we're going to do the derivative of the arc tangent of a differentiable function of x, that being u. And so you're going to get a u prime by the chain rule over 1 plus u squared. So that's going to be plus. So u would be t squared, so u prime would be 2t, divided by 1 plus, and then u squared would be t squared squared, so t to the fourth. And that'd be your k component. Okay, and then that is our derivative. So let's do one more derivative here, and we're going to look at d. So r of t is equal to cosine squared ti plus sine squared 3tj plus e to the t secant t, and that's your k component. So r prime of t, we have a chain rule, so bring down the 2, and then your base is the cosine of t, and then times the derivative of the base. The derivative of the cosine of t would be negative sine of t. That's your chain rule, so that's going to be the I component. We're going to do the chain rule again for the sine squared of 3t, so the exponent of 2 comes down, and then your base is the sine of 3t. And then we're going to take the derivative of the sine of 3t, which would be the cosine of 3t, and then times 3 by the chain rule. So you actually have a composition of 3 functions: the square function, the sine function, and then 3t. Okay, and that's your j component. And then we have a product. E to the x has the easiest derivative to remember. The derivative of e to the x is e to the x. So it's going to be the derivative of the first times the second function, which is the secant of t, plus the first function, which is e to the t. And then you might want to go back and review your derivatives for the trig functions. Derivative of secant is secant tangent. So derivative of secant of t is going to be secant t tangent t. and then that's going to be your k component. All right, so let's clean this up. So this is going to be negative 2 cosine t sine t, and that's going to be your I component, plus 6 sine of 3t cosine of 3t, and that's going to be your j component. And then for the k component, we do have a greatest common factor of e to the t secant of t, so we can go ahead and factor that out. So we have e to the t secant of t times the quantity 1 plus tangent of t, and that'll be your k component. Okay. All right, so nothing too terribly new. A lot of relying on your derivatives from Calculus 1. We're also going to be looking at antiderivatives. So if we say in the plane, if f and g are continuous on the closed interval ab, and r of t is equal to f of t I plus g of t j, then the integral of r of t dt is going to be equal to the integral of f of t dt, and that's your I, plus the integral of g of t dt, and that's going to be your j. And so these are indefinite integrals, but we're making I said it in the second, what we say for our definite integral there. But we do need the function to be continuous in order to have an antiderivative. So we make that distinction there. For the space, if f, g, and h are continuous on the closed interval ab, so we're assuming that t is on the closed interval ab, r of t is equal to f of t I plus g of t j plus h of t k, then the integral of r of t dt is the integral of f of t dt, that's the I component, plus the integral of g of t dt, that's the j component, plus the integral of h of t dt, and that's your k. If we're going to do the definite integral, so the definite integral for a is less than or equal to t is less than or equal to b, the integral from a to b of r of t dt, what you're going to do is you're going to do the definite integral for f of t, g of t, and d of h of t for the I, j, and k components respectively. Okay, so I think we got an example, three problems here, and we're going to just find some antiderivatives, and then in the second video we'll do a little bit more. Okay. So we're going to find the indefinite or definite integral. So we're going to look at the integral of 4t cubed I plus 6tj minus 4t minus 4 square root of t k. Recall the power rule for integration. The integral of x to the n is going to be x to the n plus 1 over n plus 1 plus constant of integration, provided that n is not minus 1. So we're going to add 1 to the exponent, so it becomes an exponent of 4 over 4i. Add 1 to the exponent, so t squared over 2, and that's your j. And then the square root of t is t to the 1/2. So we're going to have minus 4t, add 1 to the exponent 3/2, divide by that exponent of 3/2. Okay, and that's your k. And then your constant of integration is going to have an I, j, and a k component. So you would technically have a plus c for each one, because how we defined it, we split it up. But so when we're talking about plus c, c is actually going to be a vector with an I, j, and k component. All right, let's go ahead and simplify this. This is going to be t to the 4th I plus 3t squared j, and then plus 8/3 t to the 3/2 k. And don't forget your constant of integration, which looks like I was going to forget. And plus your constant of integration. Okay. All right, now the next one, we're going to find the integral of secant t tangent t, that's the I, plus e to the t j, plus secant squared t, and then that's your k. All right, so recall that the derivative of secant is secant tangent, so the antiderivative of secant tangent is secant, so the antiderivative of secant tangent is secant, and that's our I component. The derivative of e to the t is e to the t, so the antiderivative of e to the t is e to the t. So easy antiderivative and derivative to remember for e to the t. And derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. That gives us our k component of tangent of t, and then that's your k component, and don't forget your constant of integration. Alrighty, and we got one more, so we probably saved the best integral for last. So this is going to have some Cal 2 and Cal 1 integrals in here. Okay, so the integral of du over a squared plus u squared. I try to sneak this in at the end of Calculus 1. You'll definitely see it again in Calculus 2. So the integral of du over a squared plus u squared is going to be 1 over a arctangent of u over a, and then plus your constant of integration. Okay, so let's just focus on the I component there. So your u would be 2t, okay? So you would get 2t squared is the 4t squared you see in the denominator. Your du would be simply 2 dt, and then your a would be 1, and so we got a nice clean substitution. And so that's going to be 1 over a, so 1 over 1 arctangent of u over a, so 2t over 1, and that's your I component, all right? Now, t squared e to the t, that's a product of functions, and so our technique for integrating a product of functions in Cal 2 was using the integration by parts technique. And then, especially if we had a polynomial, we could use the tabular method, a polynomial paired with like an e to the x or a sine of x or something to that effect. We could do the tabular method. And so for the tabular method, your u is going to be the thing that repeated derivatives will end up being 0, so we'll put that as the t squared. The dv will be e to the t. So we'll start out u is t squared, dv is e to the t, and then on the left we'll take the derivative, so derivative t squared is 2t, antiderivative e to the t is e to the t. Take the derivative again, 2, antiderivative e to the t, and then once we get to 0, then we're done. Okay, and again, this is a shortcut for integration by parts. So plus, and then it's always going to go the diagonal like I've drawn there. So t squared times e to the t, and that's going to be positive. And then the next one's going to be minus, because it's uv minus the integral of v to u when you're doing the integration by parts, so you're going to have that alternating sign. So 2t times e to the t is 2t e to the t, and then plus 2 times e to the t. And if there was another one, we would have a minus down here, but because it's a 0, then it's not gonna matter what we got there. Okay, that's your j component. And the last one we're going to integrate is the sine squared of t and the cosine of t dt. So this is a trigonometric integral. It's a simple u substitution problem. So you might have seen it at the end of Cal 1, and you'll definitely see it in Cal 2. So u is going to be sine of t. Then du, differential du, is going to be cosine of t dt. And so this integral becomes the integral of u squared du, which becomes u cubed over 3 plus c, and so replace the u with what it was equal to, which is the sine. So this becomes the sine cubed of t over 3, and then that's the k component, and then plus your constant of integration. So let's simplify that down. That's going to be the arctangent of 2ti. We can factor out an e to the t, so e to the t, and then we got t squared minus 2t plus 2 for your j, and then minus 1/3 sine cubed of t, and then that's your k component, and then plus your constant of integration. Okay? All right, so this one's going to be a little bit on the longer side, so stay tuned for 3.2 part 2.